NCM Learning Center.
Good morning, friends. In this video, we are going to discuss about the how to find the RMS output voltage and RMS output current for single phase half bridge and full bridge inverters. Already we discussed the part 1 videos. In that videos, we discussed the basics fundamentals of inverters. Just refer that video. It will clearly explains the basics fundamentals of inverters. That video link is attached in the description box of the video. Okay, now we will discuss the how to find the RMS output voltage and RMS output current for single phase half bridge and full bridge inverters. Okay, let me discuss. We know that circuit diagram for single phase half bridge inverters and single phase full bridge inverters. The single phase half bridge inverter have 2 bidirectional switches, but the single phase full bridge inverter have 4 bidirectional switches. We know the basic operation of the inverters. Already we discussed in the part 1 videos. Here, for the calculation of RMS output voltage, we should know the basics operation of inverters. Here the switches T1 and T2 changes, which position changes from on to off and off to on alternatively for a fixed duration of time. Okay, so during 0 to T/2, this is a fundamental period. Half of the fundamental period. During half of the fundamental period, the T1 is triggered externally by using microcontroller or microprocessor. So T1 goes to on state. At the same time, T2 is off because it will not triggered. So the T1 will act as short because the on conditions. The T2 will off. Here the diodes D1, D2 always in reverse bias conditions. If the load is resistive load, the diode D1 and D2 always reverse bias. The diode will be forward bias when the load is inductive load, and if the inductor acts as a current source, then only it will act as forward bias on. Otherwise, the D1 and D2 always off. Okay, so the current will flow from source to there is a T1 and T1 to load. The current will flow from positive to negative in the load side. If you apply the KVL for this loop, we can get V0 is equal to Vs by 2. Okay, during 0 to T/2, the output voltage will be Vs by 2 source voltage. In the next half cycle, during T/2 T, T2 will be triggered externally, so T2 goes to on. At the same time, T1 goes to off. So the circuit will become T2 is act as short circuits because on conditions, no drop across the diode. But T1 goes off. Always diode T1 and T2 are off conditions. Now the current will flow from source to load. Then load to thyristor, then thyristor to source. This path. The current is flow from negative to positive in the load side. Okay. In the first half cycle 0 to T/2, current flow from positive to negative. In the second half cycle, current flow from negative to positive. So here V0 is equal to minus Vs by 2. Apply KVL, we can get these values. Okay, here input is DC, output is square wave. We can get this waveform in the output side. 0 to T/2, output is Vs by 2. T/2 T, output will get minus Vs by 2. Remember that for inverter, input is DC, output is square wave. For half bridge inverter, the magnitude for output is Vs by 2. For full bridge inverter, magnitude for output is Vs. Remember that. Okay. Now we discuss the operation of full bridge inverter. During 0 to T/2, there is a T1 and T2 triggered externally. So the T1 and T2 goes to on conditions. At the same time, T3 and T4 is off. No external pulse is given. So now there is a T3 and T4 is off conditions, open, and T1, T2 act as short circuits. Now the current will flow from source to that is a T1 and T1 to load, then load to T2, then T2 to Vs. This current path. If you apply the KVL for this loop, we can get output as Vs. positive Vs because current flow from positive to negative in the load side. During T by 2 T, next half cycle, thermistor T3 and T4 will be triggered. So T3, T4 goes to on conditions. At the same time, T1 and T2 off. So now the circuit will become, the thermistor T1, T2 will be open, Vs off. Thermistor T3 and T4 will act as short circuits because on conditions. Now the current will flow from source to thyristor T3 and T3 to load to T4, then source. Now the current will flow from negative to positive. If you apply the KVL for this loop, we can get V0 is equal to minus Vs. So the output will be a square wave. During 0 to T by 2 will get Vs and T by 2 T will get minus Vs. This is the operation of full bridge inverters. From the output waveforms, we can find the RMS value. Now we will discuss the how to find the RMS value for the half bridge inverters as well as full bridge inverters. We know the output waveform for the half bridge inverters as well as the full bridge inverters. Both are square wave. The only difference is amplitude. For the half bridge inverters, amplitude is Vs by 2. But for the full bridge inverters, amplitude is Vs. The calculation concept for both the inverters are same. Okay. What is RMS? Root mean square. Root mean square. Root mean square means first we have to square the waveform. Then we have to take average for the squared waveform. Finally, we have to take root for the mean of the squared waveform. Okay. First, we will take square the waveform. We know that 0 to T by 2, the value is Vs by 2. If we square that, we can get Vs square by 4. From T by 2 T, the value is minus Vs by 2. If we square this value, we can get Vs square by 4. This is the squared waveform. Now, we got to find average for the squared waveform. We know that how to find average for the waveform. Average means the basic formula is average is equal to area under the curve by period. Here period means T. Up to we got to find T, we got to find up to T period, we got to find the area. So this is a rectangular waveform. This is a rectangular waveform. The area for the rectangular waveform is length and width. Length means T, width means Vs square by 4. So area under the curve Vs square by 4 in T because area of rectangle is equal length into width. Okay, period is equal to T. If we simplify the equation, we'll get Vs square. So average value for the squared waveform is Vs square by 4. Now we have to take root for the average of the squared waveform. Okay, so if we take root value, we can get these values. If we simplify these equations, we'll get Vs by 2. So RMS output voltage for the single phase half bridge inverter is Vs by 2. Same concepts for the full bridge inverter. First square the waveform, then average for the square waveform. Finally, we have to take root. Okay, so square the waveform, we will get Vs square. Up to 0 to T by 2, Vs value. If we square that value, we get Vs square. T by 2 T, the value is minus Vs. If we square, we will get Vs square. Okay, this is the squared waveform. Now find the average area under the curve by period. Here area is a rectangle graph. So area is length into width. So we will get Vs square in T. If we simplify this equation, we will get Vs square. If we take root, VRMS value, VRMS equal to Vs. So RMS output voltage is Vs for full bridge inverter. For any type of load, remember that for any load, RMS output voltage for half bridge inverter is Vs by 2. For full bridge inverter is Vs. Just remember. Now we will discuss how to find RMS output current for half bridge and full bridge inverters. The current depends upon the output voltage. So if you know the output voltage, we can find the current. Okay, we know that output voltage for half bridge inverter and full bridge inverter. This is the output voltage for half bridge inverter. The concept is same for both half bridge and full bridge inverters. So here we are going to discuss only half bridge inverter. Okay, this is the output voltage for the half bridge inverter. The current flow depends upon the types of load. So for R load, we know that R load current follows the voltage. Current follows the voltage in phase. Voltage and current are in phase. So So the current waveform will be like that. Current is equal to voltage by resistance. I is equal to V by R. So amplitude will be Vs by 2R. The voltage amplitude is Vs by 2. Current amplitude will be Vs by 2R. Okay. Because for R load, current follows the voltage. I is equal to V by R. Now if we find the RMS output to current for this waveform, we will get I naught RMS equal to V naught RMS by R. That is equal to Vs by 2R. Because V naught RMS equal to Vs by 2. Already we find. Okay. For inductive load, we know that voltage and current relations. VL is equal to L into dI by dt. If we differentiate the current, we can get voltage. If we integrate the voltage, we can get current. Okay. So current is integration of voltage. We know the voltage. If we integrate the voltage waveform, we can get square waveform. Okay. If we integrate this output waveform, we can get current waveform like that. Triangular wave. If we integrate the square wave, we can get triangular wave. Okay. And another one point, for L load, current is 90 degree lag. This is 90 degree lag. This point is 90 degree. Current is 90 lag with voltage. Okay. So this is the current for L load, inductive load. So RMS output current, I naught RMS equal to V naught RMS by XL. Because the load have inductive load only. XL means omega into L. You know that XL is omega into L. V naught RMS. V naught RMS for the half rate generator is Vs by 2. Okay, so Vs by 2 into omega into L. Omega means angular frequency. We know the relations between angular frequency and linear frequency. Omega is equal to 2 by F. Substitute here, we will get Vs equal to 4 by F L. If it is a full bridge generator, V naught RMS is equal to Vs. Okay, the only difference is amplitude. Okay. Next, for RL load. For RL load, same, but current is exponential curve. Current is exponential curve. Current lag with voltage, but less than 90 degree. Because it have resistivity also. Okay. So the output waveform will be like that. Exponential curve. Exponential increasing and exponential decreasing. But here, for inductive load, linearly increasing and linearly decreasing. Okay. This point is less than pi by 2. Okay. So I naught RMS is equal to V naught RMS by Z. Because here have resistive and inductive load. Z is equal to root of R square plus XL square. Okay. So this is pi. Let us take this angle is pi. Current lags pi angle. Okay. So pi is equal to tan inverse of omega L by R. It's a basic formula. Next, for RC load, the current is exponential curve, but for capacitor, if it is a pure capacitor, current leads the voltage by 90 degree, but it have a resistive also. So current leads the voltage less than 90 degree. So the current waveform will be like that. Leads by less than 90 degree. Okay. But the exponential increasing and exponential decreasing. So I naught RMS is equal to V naught RMS by Z. Same. Pi is equal to tan inverse of XL by R. XL means 1 by omega C. Here XL means omega L. Okay. This is the concepts. The RMS output voltage calculation is required to calculate the total harmonic distortion factor. The total harmonic distortion factor is very important parameter to analyze the quality of the inverters. Okay. In the next video, we will discuss how to find the total harmonic distortions for the inverters. Okay. If you have any doubts related to the discussions, kindly post your doubts in the comment box of this video. Okay. Continuously watch our channel. Definitely you will get the good knowledge. And you can get good marks in the competitive examinations also. Okay. Good. Thank you.
Thanks for watching. Click the subscribe button and hit the bell icon for notification. Like, comment and share.